You are watching the Geek Nerder podcast, and we are here to make you curious and inspire you with our deep tech talks on distributed systems, databases, stream processing, and general software engineering. Now sit back and enjoy the episode. Hello everyone, this is the Geek Nerder podcast. I am your host Kaival Yapte, and I am back with another database episode. Today we are going to talk about VeniceDB, which was built and developed over the years at LinkedIn. And I'm joined by Felix from LinkedIn, who is a principal staff engineer and has made some major contributions in VeniceDB. Thanks a lot. And let's start with a little bit of introduction about your background, about what you do at LinkedIn, and what you have been currently doing.
Cool. Thanks for having me. It's a pleasure to be here. And thanks for your contributions to the community with all the episodes you publish. So, yeah, I've been at LinkedIn for about 10 years, and I've been working originally on the Voldemort open source database. And eventually we transitioned that team to the Venice project, which we'll discuss more about. And before LinkedIn, I was also working generally in the data infrastructure field. So all in all, I've been doing that for maybe 13 years or so. First as a generalist, and then a bit more specialized on the online storage part of it.
Perfect. Yeah, so happy to have you here and understand and talk about the internals of VeniceDB and the use cases that LinkedIn has solved. With any other database, I typically end up talking about the historical context, and I'll do the same with VeniceDB. So I know it was developed at LinkedIn. So what problem was LinkedIn or the team trying to solve that they end up creating a new database, VeniceDB?
Yeah, good question. We get that asked a lot because generally it's a terrible idea to write a new database. So it's a legitimate question. So as I alluded to earlier, when I joined LinkedIn, I was working on the Voldemort team, and Voldemort was you could say, a general purpose key value store, loosely based on the Dynamo paper, not DynamoDB, but before that on the Dynamo paper. And at some point within LinkedIn's history, there were essentially two games in town. We had Oracle, and if you needed more scale, we had Voldemort, and that was it. Everything at some point, everything that needed scale was built on top of Voldemort, including source of truth use cases, and then a bunch of derived data use cases. And we can dive into what derived data means if you'd like. But those included at a glance like the machine learning serving use cases, search, the graph, or rather like caching for the graph, and then some OLAP use cases as well, were at some period in time were all hosted on top of Voldemort. And then what happened is, as we kept scaling, at some point the general purpose key value store was not quite cutting it anymore. And then we started introducing more specialized systems for each of the workloads, right? Search went into a new system that we called Galean. It's proprietary, but we published some posts about it. The graph went into other systems, one called Nimbus, and then the latest one called Liquid, which we also published some about. The source of truth use cases went into a document store that we called Espresso, which there is also a paper and some posts about. And then the OLAP use cases went into Apache Pinot, which is open source nowadays. And then a few more kind of even more niche specialized systems. And then after everybody had chipped away a little part of the Voldemort workloads, right? The big major type of workload that was left inside Voldemort was the one that we called Voldemort read-only. Voldemort read-only was the use case where the entire data set needed to be refreshed frequently, usually on a daily basis, but could be at other frequencies, like a few times a day or once a week, something like that. And those are mainly the machine learning use cases. So stuff like people you may know, recommendations, and a bunch of other use cases which we broadly categorize as recommender systems, right?
Mm-hmm.
And so Voldemort read-only worked great for those batch refresh use cases. But we had several uh, challenges or annoyances, you could say, with Voldemort. It was an aging architecture in a sense. It lacked a little bit of dynamism in the sense like the topology was static. If we needed to rebalance the load to more hardware or do other such kind of operations, or even dealing with unplanned maintenance outages, basically, all that stuff was very manual and labor intensive. So that was one of the issues that caused us to rethink what should we do with this system. But then the other sort of historical reason for why we embarked on this adventure of writing a new database is that we saw a pattern where the users of the offline jobs, the Hadoop grid, right? Those users could unlock a ton of value from their Hadoop jobs and then publish the result of those jobs to the Voldemort read-only system for online serving. And that was a very productive process that helped us spin up a bunch of products like People You May Know and others. And at the time, we were in the beginning of the stream processing era, right? We had just open sourced Apache Samza. Those were really the early days. At the time, there was like Storm, Samza. There wasn't a lot more out there, right? And we thought that stream processing was going to be a big thing. It was not really a big thing yet, but we thought it would be. But there was not a very good sync for the output of stream processing jobs at the time, right? You could have the last hop in your stream processing job write to a MySQL or a Redis or some sort of system like this, but it was a little bit janky. Like you had to write a lot of glue code, and then the correctness and reliability properties were not very well defined. Like you might have gaps in your data, or there could be a bunch of gnarly issues. And so we wanted to essentially, it's a long winded way of getting to the following point, which is that this new system, Venice, we wanted it to do for stream processing what Voldemort read only had done for batch processing, right? Which is to unlock the value that's been generated in those processing jobs in a way that the output of these jobs can be served online at low latency. So that's the gist of it. Hopefully that makes sense, but I'm happy to drill down if you have any questions.
It does makes a lot of sense because it gives an historical context, like how Voldemort key value database was used for all these use cases. And then slowly, when there were some issues like scaling and operational overload, some of these use cases, like well-known technologies like Apache Pinot and Espresso, all these use cases were more specialized use cases and similar to what we have for the batch processing use case, as you mentioned. And if I understand correctly, Voldemort read only was fine for daily updates for bulk processing jobs, but it wasn't really good enough for stream processing results. And I think it makes sense. And I'm also getting a sense of what does derived data mean. But I'll still ask you the next question, which is derived data platform, which is used as a terminology for VeniceDB. So, what does derived data mean here? Is it just a result of any pre-processing that is done, or it means something else? And you mentioned a couple of examples like People You May Know and some other features or use cases on LinkedIn. So, it would be nice if you can also take some examples from there.
Yeah, good question. So, by the way, if anybody wants to learn more, I did a talk specifically on this at QCon London in 2023 called What is Derived Data and Do You Already Have Any? But the gist of it in a nutshell is derived data is data that has been derived from other data. Now, what does derived mean? It could mean a variety of things. It could be a physical transformation of the data, meaning that the data is conceptually the same, but it's organized in a different way that is more optimal for a certain use case, right? For example, what happens inside OLAP systems such as Apache Pinot is that they're going to adopt some kind of columnar layout. It's still the same data, but now it's more efficient for scanning the whole data set, and that gives us the ability to perform aggregations or that type of stuff in a more performant way. Another flavor of physical derivation could be that we are producing a materialized view which joins many input data sets, right? Because again, for performance reasons, we don't want to go out and fetch from 12 different tables and put a lot of burden on 12 other databases. So instead, we'll cache this joined view that we very often need, but maybe we don't need to have in a strongly consistent way. It's okay to have a little bit of delay for that cache, right? So that's another example of a physical derivation. Then another bucket of use cases is where there's going to be a logical derivation. So the output is conceptually different from the input, right? It could be a very slight logical derivation. For example, in a search system, we might do tokenization, right? Which could be that we strip out the plural or we swap certain terms for their synonyms, and that helps us get better hits. Those are like fairly simple strategies where the output is still fairly similar to the input, but just a little bit optimized for the use case. And then there are certain types of logical derivation where the output is completely unrecognizable from the input. So I would say the machine learning use cases often fall in that category where the input might be, let's say, a bunch of events representing interactions between users. Let's say they liked each other's posts or sent each other messages or any sort of activity. And then the output of that is an affinity score, right? So it's just a value between 0 and 1 that represents the likelihood that these two people are engaged in activities with one another. And so from the output, there is no way that you can really understand what is the input that went in. It's like some kind of opaque transformation. So all of these various types of derivations fall within the category of derived data, essentially.
Okay, yeah, that makes sense. And I have a good understanding of different use cases that you mentioned, having personally used LinkedIn that even closely relates to it. Just taking another example, for example, I have to find folks who work at a certain company and who have searched for something and those kind of stuff, right? Because there is multiple events happening, like people are connected, people are searching for something. So these are search events and then connection events, and then probably they work on certain technology and different types of filters I can have. And then based on all of this data that I have in different data stores, some machine learning job would figure out some affinity score, for example. And then that is the derived data. That's the value of some operations that the machine learning model is doing. And that is stored here in VeniceDB. Okay, that makes sense. And before we go a little bit deeper, there was also another term I would like to understand better. It was mentioned like derived data platform for planet scale applications. What does planet scale mean?
Right. Good question. At LinkedIn and at many other companies at this point, one of the considerations that is always in the back of our minds is that we operate our stack spread across multiple regions, right? And we do that for various reasons. We do it for load balancing purposes because it's just not practical to have that much capacity in a single place. We also do it for reliability reasons. We want to be able to serve our traffic out of two of our three regions, basically. So one region can completely fail out, and the traffic will get failed in the other regions. So that's something that we have continuously happening. Every week there will be fail-ins and fail-outs. We even trigger them intentionally just to test that we still have the capacity to serve the workload, because as the workload keeps increasing, it's not good enough that last month we were able to fail in. We have to retest that, and especially as every team is making changes, there could be new bottlenecks or regressions that we wish to discover sooner than later. So that's something we do continuously. Now, what it means in terms of system design is we wish to absorb as much of the complexity of running across multiple regions, as much of that complexity as possible into the infrastructure, right? So that the application teams, which are higher up in the stack, can leverage powerful building blocks without needing to think too much about the issues of being a multi-region service. In practice, we cannot completely hide all of the complexity, but we try to make it as easy and productive as possible, right? And so Venice is one of our several replicated systems. It has a first class support for replication of all of our workload types, right? So we, in Venice, for example, the workload types are batch refresh of the data, but also streaming writes. And then in addition to that, combination of batch and streams into a single data set, which we call hybrid, right? So all of these, and then even within those, there are some finer subcategorization we could dive into if you'd like. But the point is, all of these operation types are all built in a way that they will be replicated, and not only replicated, but replicated in a way that is coherent and makes sense, right? So that we guarantee that we achieve eventual consistency, we don't have data loss, and so on.
Interesting. Yeah, that makes sense. Coming back to our previous points, as you mentioned, that this is a derived data platform, which means something else is deriving the result from many data sources or a single data source. And that derivation can be logical or physical, but that derivation may result into like different types of data sets, right? For example, affinity score can be just a number, but for some it could be like a different data set. For it can be like a JSON file, or I don't know, JSON document, or for some it can be a key value pair. So if I understand correctly, it could be like different types of data structures that you would want to store in VeniceDB. So I would love to understand, with talking about the right path of the VeniceDB, like how these things come into picture and how do I write data into VeniceDB?
Right. In terms of writing data into Venice, so the first thing to keep in mind is Venice is a strongly typed schema aware system. And so it can be used either as a key value system where the key and the value both have a predefined schema, or actually, in the case of the value, it is a set of compatible schemas, right? Because we do support evolution. In addition to that, there is also a document store type of API where you can choose to project only some of the columns of a row, or fields of a record is another way of saying it, when reading data out. And then when writing data as well, you can also choose to update just a subset of the columns of the row rather than writing the whole row at a time. These are, at a high level, the APIs that are supported. And when writing data, as I alluded to earlier, we have essentially three types of sources of data. We have the batch only workloads, where the whole data set is going to be fully refreshed on a periodic basis, could be daily or several times a day. And then we have the uh, pure real time workloads, where the data comes only from streams. Essentially, stream processing jobs is the main case here, but we also have nowadays a library that allows you to write into Venice from any application in a producer style, like the Kafka producer, right? Meaning that the write is still asynchronous, it's still going into a stream, but you don't need the whole machinery of a stream processor. You can do it from any runtime. And then there is the combination of these two, which we call hybrid. So you can have periodically a batch job that will refresh the whole data set. And meanwhile, you also have streams that will update either all of the columns or a subset of the columns, right? So you can essentially pick and choose. For example, you can have a batch job that periodically refreshes everything. Let's say you have 100 columns in your table, but then there's, let's say, 10 of the 100 columns that you feel are very high value to get in a fresher manner. And so you go ahead and build a stream processor for updating these 10 columns only. So you don't need to pay the cost of writing the stream processing job for all the columns. You can pick and choose and do it just for the ones where freshness is most important. And then if you do that, Venice will take care of merging all of that together uh, in a coherent way that works out of the box, basically. So these styles of architecture where you have both a periodic batch refresh as well as streams coming into the system are sometimes called lambda architecture. That's a term that's been coined by Nathan Mars, if I'm not mistaken. And then later on, Jay Krebs did a spin on that and said, what about instead of lambda, what about having the kappa architecture where the same idea, but both the batch part and the stream part can both be implemented with stream processing technology. So then you have just a single processing stack. And all of these essentially design patterns are supported by Venice. We support Lambda architecture, Kappa architecture, and then batch only and stream only.
Okay, interesting. So this makes it clear like how you can ingest data into VeniceDB depending on your use case. So batch only, hybrid where there's a job running periodically, updating something in a batch or bulk format, and then there's real-time streaming events that are coming and they're updating the data. And then the third one is stream only, where there is only real-time event coming in and updating some records or processing or storing some records. That makes sense. And you talked a bit about how these merging takes place when you are using it in a hybrid manner. And I have used some, or I have worked with some Lambda architectures, never really worked with Kappa. And I've also faced some issues. There's always some issues when you try to have some stream processing, but for some reason, you cannot process that data in real time because, let's say, missing data or you're just waiting for some event. So you do it at a later stage in a bulk manner, and then you try to update. So help me understand how this merging takes place and how Venice DB on what parameters does it decide that, okay, this is the right way to merge these two data sets? Because they might be updating the same data, right? If I'm not mistaken.
Good question. I think it may be worth just taking a slight step back and explaining how is a Lambda architecture traditionally implemented, right? Because in Venice, we took a slightly different approach. So I think the original way that the Lambda architecture was pitched was you have essentially two completely independent pipelines, right? You got a batch pipeline and then a streaming pipeline.
Yeah.
The batch is going to perform some batch processing jobs, and then it will throw the output of that into some batch only sync, which could be Voldemort read only, or several companies had like kind of proprietary technologies for doing that. And then on the stream side, you got a stream processor, Storm or Samza or Flink or whatever, and then you got the output of that going into some mutable store, right? So it might be like MySQL, Redis, whatever. And then the key thing is the online application that wants to read this data needs to do a dual read. So it will read both from the batch store and what is sometimes called the speed layer, right? The mutable store. And then there needs to be some sort of reconciliation logic, right? Let's say, for example, it might be if I find the record or the key I'm looking for in the speed layer, then I just take that and ignore the other. And then the batch only result is like the fallback, or else there might be some kind of timestamp that is checked, where you take the higher timestamp because in certain edge cases it might be possible the batch store actually has the more recent data for some reason. Let's say there's been some failure on the streaming side or whatever.
Yeah.
So that's the way it's been implemented in the past. Probably still many people do it this way. In Venice, we wanted to take a different spin on this. And the reason is that we felt the Lambda architecture has a lot of moving parts that make things a bit complex. And when you defer the merging to the read time, then you have a few issues there. Your reliability becomes the worst of both, and your latency becomes the worst of both. And so the extra moving part is like not serving you that well. And so in Venice, what we wanted to do is offer a way out of the box of orchestrating the merge of the batch data source and the stream data source so that the merging happens at write time. So ahead of time, basically. And then the pre-merged data is hosted there inside Venice so that when the application reads, it does just a single query, gets it back. And so there are fewer moving parts, fewer things that can go slow or wrong. And so that's the general idea. And the way that we built this essentially is there is a important configuration. There's basically a single configuration that the user needs to think about for their use case, which we call the rewind time, right? So what the rewind time means is in their hybrid use case, after they're done ingesting the batch data into Venice, Venice will do a look back inside of a real time buffer, which is essentially a Kafka topic under the hood. And it will replay however many items from this buffer corresponding to the rewind time. So, for example, you could say, I want a rewind time of 1 day or 1 hour or whatever it is. And the point here is by the time the batch push even begins, pushing into Venice, at that point, the content of the batch push is already stale in a sense, right? Because that data is the output of some processing jobs, which could be the output of other processing jobs. It could be like a complex DAG of processing, right? And then the leaves of that DAG are the sort of input data sets, which could themselves be stale. Let's say they're ETL'd from some other database or wherever they come from. And so it's very common that these types of pipelines are going to produce a batch data set which could be several hours old already because the processing took that much time. And so that is the purpose of the rewind time, essentially. The rewind time needs to go far back enough in the real-time stream so that there is no data gap. There is no need to make it go exactly to the cutoff point. It just needs to go farther back. And then what happens when pushing to a hybrid store is that there is this real-time buffer replay based on the rewind time, and the events in the real-time buffer get applied on top of the batch snapshot, right? And only after the buffer replay is complete will we start serving traffic out of this new version of the data set. And that's an important concept right there. In Venice, we don't have just data sets, we have versioned data sets, right? So whenever a batch push occurs, Venice will dynamically instantiate a new version of the data set. And then there is a pointer where the read traffic is going to go to the current version of the data set, while a future version of the data set is loaded in the background with minimization of the interference of that activity and so on. And only when this batch bulk load is complete and fully checked with integrity checks, checksums, etc., only after everything checks out do we change the pointer to the new version of the data set. So that the read traffic starts hitting it. So that's the methodology. And all of that is orchestrated out of the box, right? The user doesn't need to do any of this. It's just supported by the system.
Interesting. I think I understand this at a high level, but I have some questions there. So
Mhm.
specifically on the rewind time. So rewind time, if I understand correctly, it's mainly used to figure out if the results from the batch job is basically fresh or it's stale. So you can just ignore that, right? Is that correct?
Yeah. So I think conceptually it's correct. If we go just one layer deeper, we could say the content of the batch push gets ingested no matter what,
Hmm.
but then some of it may get overwritten by
Yeah.
the recent streaming rights.
Yeah. Okay. Okay. That makes sense. And if I understand correctly, the rewind time is basically done on a buffer, which is a Kafka topic. And does it closely relate? So the rewind time that I might have to set, does it closely relate with the batch job frequency? If the batch job is running, let's say, every 4 hours or 2 hours, does it make sense to have it close to this time period or there's no correlation?
It should be at least that long,
Okay.
right? Because if the rewind time is too short, then you risk having a gap in the
Yeah.
data.
Yeah.
Um, so it's not really that important to make the rewind time super tight to
Mhm.
minimize it. We just want it to be large enough. And then the, the only reason why we might want to minimize the rewind time is in case, in very specific, like niche cases where the streaming traffic is extremely high throughput and we happen to have a good handle on how what is the maximum staleness of the batch part, then we can optimize a little bit by making the rewind time shorter so that the real-time buffer replay phase will take not as much time to complete.
Yeah.
But that's a bit of a power user optimization, which for most people doesn't really matter. So the main point is just to make it large enough that there is no gap.
That's a good recommendation. And I was actually thinking on the similar lines that if rewind time is, let's say, I don't know, 2 days, and you have to
Mhm.
rewind all the events and figure out if the batch processing results still make sense or you it can be overridden. I think it might take a bit longer. So the point of the consistency, it is closely relates to this point, right? Like where my new version will be created once I have the result from the batch job, and then the time it takes is it depends on the rewind time setting. If my topic has like ton of events, as you mentioned, for a power user, it might be longer. But I think for majority of the use cases, this will not be that of a huge topic to replay when it comes to rewind time, right?
Yep, that's right.
Okay, perfect. And what's in this topic? Is it the actual events that is coming from the speedy lane, or what's there in the topic?
Yeah, good question. So we have this real time buffer topic, which is essentially an internal implementation detail, right?
Mhm.
The user does not need to provision this topic or configure it in any way. It's all happening automatically when the Venice resource is provisioned, and Venice makes sure that all the internal pieces are in place.
Yeah,
So, for all intents and purposes, this topic is hidden from the user. It has Venice's own protocol for encoding the data in it. And this protocol supports all of Venice's write operations. So those include the full put, which means for a given key, overwrite the whole value, delete. So for this key, delete the value. And then we have a third category, which is a partial update, essentially, where you can mutate just some of the columns of the row, or within that framework, we also have collection merging operations. So if the schema contains a collection like a set or a map, we can add entries or remove entries from these collections. So these are the types of operations that are modeled inside of the real time buffer topic. And any of these operations can be applied on top of whatever was provided by the batch push.
interesting. Okay, that makes sense. And I have one more question on the merging process, and then we can move to a different topic where we go deeper and understand what is exactly happening. So, when would be a case when the merging, let's say, fails, when VeniceDB is not able to decide which one is the later version? Is there a case like that, or it will always be able to resolve in some scenarios? And from the user's perspective, if I have to figure out if the merging is happening correctly, I'm not sure if as a user I have to do something, I have to configure like how the merging should happen, or it's totally based on times, like the timestamp of the events and the batch processing. So
Right.
I guess what I'm trying to ask is, what happens if the merging fails, and how does VeniceDB figures out that this is a later event and this is not?
Right. I would say in normal operations, there is no merge failure, right? If there is a merge failure, that would be a bug, right? It's not a bug of the system. It's not expected that there would be failure. There is always a resolution outcome, right? The resolution outcome is based on a timestamp, which by default is what we call a physical timestamp. So that means it is taken from the clock of whichever process produced the write. So that's the default. We also provide the option of a logical timestamp, which means that the user can specify for a given write what is the timestamp they want. It has to be numerical, and we just take the higher one. The use case for doing logical timestamp is, for example, you could plug in there the value which corresponds to your input, right? So, for example, if your input is change data capture from another database, you might want to have the derived output be timestamped with the timestamp of the source of truth database that it came from. And what this allows you to do is that if your stream processing job that consumes this change data capture went down for some period of time and is then catching up on lag, you might want the output event to be tagged with the older timestamp of the input, right? So that the resolution takes into account that those are lagging writes. Another example might be that you pass in the offset of the Kafka topic, which serves as input, for example. So those would be examples of leveraging the logical timestamp. In that case, it doesn't even have to be a timestamp per se. It just has to be a number. And so we support both of these. And then we have a certain deterministic rules in case of ties. We have some tie breaking logic. And you have to keep in mind, going back to the what does it mean to be a planet scale system and operating on multiple regions, we actually have the merging logic running concurrently in all of the regions, right? And so it is critical that the leader replica that exists in each region comes up with the same conclusion as the other leaders, right? So it is a multi-leader system, essentially. And so we have these deterministic rules, which are loosely based on the CRDT literature, the conflict-free replicated data types. And so we always have a deterministic outcome, even if the writes may be processed out of order in one region compared to another, right? So all of our operations are idempotent and commutative, essentially. So that's the gist of it. Now, maybe taking just a slight tangent, while there is never a merge failure, there could be other types of failures, right? So, for example, there could be some data loss coming from the pub sub system we're using, like the Kafka layer, right? And so we have ways of detecting that, right? So within the Venice protocol, we have like sequence numbers and things like that that allow us to detect if there's been a gap. And then depending on the case, we may, in all cases, we will for sure have like alerts firing if that is detected. But furthermore, if it's detected within the batch loading phase of a push, then we actually fail the push, right? Because there's been essentially an integrity issue with the underlying infrastructure. So we want to bubble that up to the user, let them know this push is not actually good to go. We got to kill it, unfortunately. Whereas in cases where the writes is coming into the currently serving version of the data set, we don't have the luxury of killing that because it is serving live traffic. So the show must go on, so to speak. So we will still fire alerts, investigate that with our infrastructure partners and so on. Um, but we will have to keep serving that data set even if it may have suffered data loss. So this is essentially the way we detect and handle failures. Although the merging logic per se, it is always going to succeed one way or another based on the specific rules.
Yeah, that's fair enough. And I think it also makes sense. And since you already touched some of the architectural components, let's move on to understanding the architecture. Like, what does the architecture look like? And when we talk about the right path, like, what are the components involved? And how does the data gets persisted and where, in what format?
Sounds good. So within the right path, you could think of it this way, right? We've got sources of data, which could be the push job for batch data sets, or some stream processing jobs, or even any random application that packages our producer library, as I was saying. In all cases, all of these writes get funneled into a pub/sub system, Kafka. And then on the other side of that, we have the Venice server, which ingests that. And I glossed over some details earlier, but essentially the gist of it is a given Venice resource is made up of several Kafka topics, right? There is a real-time buffer topic, but then there is also some other topics, which we call the version topic. And there is one version topic per version of the data set, right? And these version topics contain the output of the merge function, essentially. Mm-hmm. So we have a leader follower architecture. The leader replica is the one that is consuming from the real-time buffer topic and executing the merge logic. The output of the merge logic gets written into the version topic, and then the follower replicas consume that and apply it without any further logic, just blindly apply it, right? And we also have some clients that can hook to these version topics and pre-materialize the local cache of the data set, for example, based on that. So the followers can be either like Venice servers, or in some cases, client libraries also have the ability to consume those. And then we leverage RocksDB for persisting the data in both the leaders and the followers. And we leverage RocksDB in a couple of ways. We have RocksDB has a block-based format and a plain table format. We leverage both of those for different workloads, right? The block-based format, which is basically the default format, is ideal for SSDs with a little bit of hot data that gets cached in RAM. And then the plain table format is optimal when you want the whole data set to fit in RAM for even better performance. So we have the need for both, and we pick and choose whichever we would like to use based on the workload. So at a glance, these are the components involved in the right path.
Interesting. Okay, so there are leaders, and whenever data is coming in, leader is the one that reads the buffer and tries to do this processing and figures out after the merge what is the result, and then writes to the version topic, and then that version topic is basically the sink for the leader. And then the replicas are just reading from the version topic and storing it in a local, embedded RocksDB instance, right? And that's where the result is stored. Okay, interesting. And how are leaders like partitioned? These are partitioned based on certain ID or what field based on the data, and how I as a user can configure that?
So we have a default partitioning scheme, which for most users, they will not need to configure that. Essentially, it's just doing an MD5 of the key, and that decides the partition, right?
Yeah.
We have some power users that for one reason or another need to configure the partitioning scheme. And that is for a use case that I only alluded to earlier, but we didn't really talk about yet, which is we have one of our client libraries that we call the DaVinci client is a stateful client. So that one like I was saying earlier, consumes directly the version topics. And so instead of doing remote queries against the backend whenever it needs to read, it can read directly from a local RuxDB copy of the data. And that keeps getting updated continuously, right? So that provides even better performance. And if using DaVinci, there are essentially two design patterns. You can either subscribe to all the partitions. That's the easiest way to leverage this offering. But if you do that, then you need enough resources provisioned on your local box to hold the entirety of the data set, which in some cases it's fine. Like the data set might be just a gig or 10 gigs. That's okay. It fits comfortably in RAM or on a local SSD even. Some of our power users need to partition their DaVinci application. So in that case, they will subscribe to specific partitions, and then they have a need of controlling the partitioning scheme in that case, right? So an example of that is within our search system called Galean that I mentioned in the beginning, we have the inverted index, which serves to retrieve documents that contain a hit for a certain term. But then there is also a scoring and ranking phase because typically there are way more documents matching the search query than we can ever show, right? And so we have to return only the most relevant ones. So what the search system does is it embeds a DaVinci client, which will provide it with the machine learning feature data that it needs for its scoring to occur. And therefore, it's important that these machine learning feature data are co-partitioned with the inverted index. So both of these data structures are partitioned, and you got to have the same shard on a given box. You can't have like partition 1 of the inverted index with partition 10 of the ML feature data. It will not work, right? So that's a pretty advanced use case, but it is one that Venice supports as well. And so in those cases, we do allow configuring the partitioner, which in that case, the partitioner is still always based on just the key part of the payload, but it could implement a different algorithm than the default one using MD5. And in some cases, the user looks at just a portion of the key, right? So they may want to, they have a composite key made up of several fields within it, and they want to partition according to just some of the fields, not the others. So these are all supported if using the custom partitioner.
Okay, that makes sense. So in short, like the general partitioning strategy should work for most of the use cases, but for specific use cases, there is some support people can configure it. That makes sense. And with the DaVinci client, I guess we've talked a bit about how the reading part works, right?
Yeah. So in terms of reading client, we've got essentially, you could say, two clients. We've got like classical Venice, which is the one that does queries to the backend. So for each key that you want to read, it does a query, or you might want to query a set of keys, right? So it will batch get all of the values
Yeah.
associated with this set of keys. And so you got the network in there. And so we still try to make it as performant as possible. And in fact, it is performant enough for the vast majority of use cases. But in certain scenarios where the user needs even more performance and they are willing to provision the resources for holding the state locally, then they have the option of the DaVinci client as well for that. And the general design philosophy here is that these clients should have the same API, right? In practice, the DaVinci client is a superset of the API because there is a little bit extra to specify how you want to subscribe to the data set, either subscribe to all partitions or specific partitions. But that's the only difference, basically, right? And you can code your application against a single API, doing essentially a single get, batch get, or some limited form of computation, let's say projecting some field out of the data, or we also support a little bit of vector math operations that the machine learning use cases sometimes need. All of these read operations are supported by all of the client library options, right? So you can swap that later down the line, right? Like the easiest way to get started is with the stateless client that will query the backend. But if later down the line you need even better performance and you're willing to pay the cost for it, you can swap that out for the DaVinci client. And there is very minimal code change needed. You just need to tell it what to subscribe, basically. The rest of the application remains the same. Does that make
Okay.
sense?
I think it does. And if I understand correctly, that the read patterns that are supported is key value lookup or a range or a set of keys that you can look up for a set of values. You can also filter some of the fields that you want based on depending on the value. And there's also some vector operation support, as you mentioned, for the machine learning use cases. Is there any other query pattern if I have to filter based on like the value of or a certain field of the value? Does it mean that I can also do, let's say, pattern matching on a field, on a value, or that kind of use case? Is it also supported?
No, those are not supported. So the access pattern is always, you could say, lookup oriented,
Mhm.
right? So you've got to provide the key that you're looking for, either a single key or a batch of keys, but you have to provide them. And then optionally, for the values returned for these keys, you can have a little bit of lightweight post processing, projecting just some of the fields out of the record or transforming a, let's say, a vector of floating point values into a scalar like single float based on some input for the computation, right?
Okay.
Those are the supported ways of querying data out of Venice. We do have a slight addendum to that. Well, actually, we do use it in production, so I wouldn't call it like completely experimental, but it's not like widely used, I would say.
Hmm.
Within the DaVinci client only, not in the other client. We do have the option in there of scanning the all of the records that exist, which so you can either scan everything or scan according to a prefix of the key, right? So if your key has multiple fields, you can scan by limiting the left hand side fields of the schema, right? Because of the way the data is laid out. And so there is this sort of limited support for scanning, but I would say that's, yeah, like I said, it is used in production, so it works, but it's not like the primary use case, I would say, that is best supported. We have thought about adding more powerful filtering capabilities in the past, and we might still go there at some point. The use case being like, let's say I have a batch get where, let's say, I want to retrieve 5,000 keys, but I know for sure that if some field of the value contains a given value in it, then I'm going to drop that record anyway. I'm not going to look at it. So you could do this filtering server side to reduce the bandwidth cost.
Yeah.
We don't actually support that as of today.
Okay. Okay.
But we have designed that in the past, and then in the end, the use case didn't materialize. We didn't end up building it, but in theory, we can. And if there's anybody interested in some challenge, contributions are welcome, of course. As of today, that's not supported.
Okay, that makes sense. And so, if I can understand correctly, these are like lookup based queries that clients can make. And since I guess the partitioning strategy is very simple, the client knows where the leader is for this particular key and it can connect to that and read the latest version, which is ready to be served.
Yep.
Okay. And for bulk gets, so let's say I have, I don't know, 5,000 keys, and then depending on the keys, I might end up hitting like multiple leader nodes and getting data from there. And in failure scenario, or not the leader, right? Because this is just reads that are happening. So I can read from the followers. Is that correct?
That's right. Yeah. We
Okay.
don't actually direct reads at the leader specifically. We use any of the replicas.
Okay, so the read scale with the replicas for or the followers for each of the leaders, and then the client can maybe end up connecting, I don't know, 5 different follower nodes to read all these 5,000 keys, and then at the end, the result would depend on all the 5 followers being available, right? So how does the fault tolerance works internally behind the client?
Yeah, that's a good question. So by default, right, when using the batch get API on the client, we provide an all or nothing semantic. meaning that if we successfully retrieve all of the keys, some of the keys are allowed to not have a value, right? But we would know that, right? We would have gotten a successful response indicating these are the keys that exist, right? By default, we will only return that result to the application if we got successful responses. And of course, like if some replica is unavailable, we do have retries to try the other replicas within certain bounds, right? We will not retry forever, and there is a latency budget that if we go over that, then we'll give up. That's how it works by default. It turns out that this is not always the most useful semantic, right? Because in these recommender systems that I've been mentioning, so essentially, just as a small parenthesis, let me tell you what a recommender system is, right? A recommender system is one where you have some candidate items that you might want to show. Those could come from anywhere, right? There's a variety of ways of generating the candidates. But then you have too many candidates, so you need to score them, right? And what you're going to do is you're going to retrieve some machine learning features for each of the candidates, and you are going to feed that into some model or potentially even just some business logic if it's a simpler use case. And then the output of that is some score for each of the candidates, and you rank that and return the top K highest scores, right? That's the gist of it. Now, what I was going to say is it turns out that for many recommender use cases, they would much prefer serving something than serving nothing, even if it's based on incomplete data. And in addition to that, recommender use cases are sometimes extremely latency sensitive because they want to fit within a certain latency budget their end-to-end work, which includes retrieving, first generating the candidates, that takes time, retrieving features for each of these candidates, and then actually scoring them. And in an ideal world, the first two parts would be extremely fast, and there would be as much time left as possible for the scoring, which would be the most expensive part of the workload, usually, not necessarily always. And so they have a super tight latency budget for the feature retrieval part, which is the part that involves Venice, right? And so what they would like is to specify a timeout where whatever we manage to retrieve during that time, they would like to get it. And so that could be a partial result. And so that's another API that we provide. Essentially, you can choose either the all or nothing or the partial response capable API. And that can give you sort of more tools in the toolkit depending on your needs.
Yeah, absolutely. I think it depends on the use case. Uh, cool. So I have one more question on the read side. Since we were talking about the versioned aspect of the values for any key, do I have the ability to read like a history of values for a given key? Since I have the version anyways, can the user get different versions, let's say last three versions of how a particular value has changed for a given key? Is that also supported or maybe in the future?
Yeah, so we sometimes refer to this as time travel capabilities,
Yeah.
right? Which stuff like, let's say, Iceberg supports and stuff like that. In Venice, we don't have time travel. So just to clarify, the versioning, so there are maybe two different notions of versioning that could get conflated. So it might be worth disambiguating them, right? So there is the merge logic that we talked about, where you have, let's say, full puts and deletes and partial updates and collection merging, write operations, all potentially affecting the same key. And we want the leader of each region to deterministically choose an outcome for all of these operations coming in. And in order to do that, it leverages timestamp, which, as we said, can be either physical timestamps or logical timestamps provided by the user. And so this timestamp can be viewed as a form of version conceptually. However, we only expose to the user the latest such version. In certain cases, we do keep a trace of other things like tombstones, right? So a key that's been deleted will return null if the user attempts to read it, but internally we do keep a tombstone indicating the timestamp at which it was deleted, which is necessary for deterministic conflict resolution. But that tombstone, as of today, is not readable by the user in any way. It's an internal detail. And so time travel is not supported in that fashion. You always get only the latest version. There is another notion of versioning that we talked about, which is the dataset level versioning, right? Which is where when a full push occurs, Venice will dynamically instantiate a new version of the dataset, and then there will, during some period of time, there will be like a current version of the dataset, which is the one serving the read traffic, and a future version of the dataset, which is the one getting bulk loaded in the background but doesn't serve a read traffic yet. That notion of versioning is also not exposed to the user, right? So it is just an implementation detail of how the write path is orchestrated, but the user, as of today anyway, does not have the ability to specify which dataset version they want to read from. They always read just from the current. So yeah, so hopefully that answers the
Yeah,
question.
I think it does. Yeah. Since we also talk about the Kafka topics, there is this buffer, then there is the version topic, and probably some other topics as well if we talk about internal details. So how does Kafka comes into the picture when I look at from a deployment perspective, right? So when I deploy VeniceDB, is Kafka embedded within, or do I have to have a separate Kafka cluster and then give it the broker link, and then VeniceDB can work on top of it? How does that work?
Yeah, good question. At LinkedIn, as you can probably imagine, we have a ton of Kafka clusters, right? That we last time I think I heard we had 80 different Kafka clusters or something like that. Venice has a dedicated Kafka cluster in each of the regions, right? So the Venice deployment of a region is tightly coupled to the Kafka cluster of that region. And well, in fact, you could say it's a full mesh in the sense that the Venice deployment will produce into the local Kafka cluster only, but it will consume from all of the Kafka clusters, local and remote, right? Because it is performing these merge operations on the
Mhm.
data that could come from anywhere. So that's the deployment topology. For someone picking up Venice and trying it out, I think it would be safest to mimic that deployment style, which would be to give Venice a dedicated Kafka cluster. In theory, it could be possible for Venice to operate within an existing Kafka cluster that has other non-Venice workloads in it, but this is not the way we use it, and so there may be edge cases, and those could potentially be serious edge cases in the sense that, remember I said that the batch push results in the dynamic instantiation of a new version of the dataset. That new version of the dataset has an accompanying version topic, right? And so in normal operations, Venice continuously creates and deletes Kafka topics, right? So the cluster, the Kafka cluster that Venice owns, so to speak, is a bit of a special kind of Kafka cluster. It will not really look like your typical Kafka cluster, right? In a typical Kafka cluster, you have time retention based topics, and the topics are long lived, right? That's the typical scenario. Within Venice, there is a mix of topics. The real time buffer topics are similar to what I just said. They have time based retention and they're long lived, but the version topics churn. So they get created and deleted frequently. So, for example, at LinkedIn, we have over around, I would say, around 2,000 push jobs per day. And so that means there is, in effect, 2,000 topic creation and 2,000 topic deletions per day happening on the Venice Kafka cluster. In fact, it maybe an interesting historical tidbit that a decade ago, deleting a topic in Kafka was pure hell. Like it at first, Kafka didn't even have an API for deleting a topic. You actually had to. So I did this actually at my previous job. You had to do a rolling bounce where while the Kafka broker was down, you went and deleted files in the file system, then brought it back up, and you had to do that for all of the brokers. That was the way you deleted topics originally. Then they bolted on some delete topic command, but it didn't work very well, had a ton of bugs. And actually, I would say because of the development of Venice, there is a ton of delete topic bugs that have been uncovered and fixed. Um, and so, in a sense, if Kafka has the ability to delete topics at all today, it implicitly it is probably because of Venice. Or if it would have happened on its own, at least Venice accelerated it by several years. That's something that probably very few people know, but yeah, delete topic was terrible before Venice forced it to actually work.
That definitely sounds terrible.
So yeah, nowadays delete topic works great. But coming back to your question, I would say for now the recommended deployment style would be that the Kafka cluster should be dedicated to Venice. That's probably the safest way to operate.
That makes sense. Cool. Let me guess, and you can correct me if I'm wrong, that probably it is named Venice because of all the different streams of data coming in, and it looks like the beautiful city of Venice. So, is there also some historical context that you could share?
Yeah, in terms of the naming, we actually agonized over it for a while. At first, like we called it like the derived data system or something, but that was a mouthful. Yeah, at some point after many brainstorming sessions, I think it was one of our interns that proposed that name, and everybody was like, "Yeah, that sounds great." And yeah, that intern actually has the very first commit of the Venice repository. His name is Clement. So yeah, so he contributed the initial commit as well as the name, very significant contributions.
Perfect. Yeah, quite a good name. If I remember correctly, it was open sourced in like 2021 or 22. And so what's the roadmap like? What active work is going on in the VeniceDB community, and what's coming up?
Yeah, I think the reality is when running a massive scale system, there is a very large fraction of the work that goes into just polishing the system. A lot of the work is not really going into flashy new features, so to speak, but really just buttoning up everything, making it cope with the increases in scale, which are significant for us. But we can still, within that, come up with a few themes of areas we're investing in. For example, a big area of focus right now is providing a better write latency SLA to our users. So up to now, the latency of writing data into the system has not really been a big concern for the majority of users because the data is already processed asynchronously anyways. What does it matter what the last mile is? And so that we have relied on this assumption for many years that this was not the most important thing to optimize. But now we are starting to have certain use cases that are more sensitive to write latency as well. And so we're going in and making sure every part of the system is prioritizing the most latency sensitive workloads. And then we have certain things like when a leadership handover happens, there are certain delays involved with that. And so there's a bunch of little details that mean that even though our average latency may not be that bad, like maybe a second in most cases, in the long tail, it can spike up way more than that. So that's an area of focus. Um, some other areas that we're working on is in terms of the read path. We didn't really go into a lot of details there, but we actually have an ongoing transformation there in terms of how data gets accessed remotely. So in the classical Venice mode, right? The original architecture is you could say a 3-tier system. You got client, router, server. The router tier is stateless and performs the routing, while the client is a so-called thin client, very simple, doesn't have to be partition aware. This has served us well for many years. It's easier to operate, very maintainable, but it does mean that the read path has two sequential network hubs, right? From client to router and then router to server and then back. We now have a new client that we call the fast client as opposed to the thin client. And that one has a partition awareness. And so it can route directly to the correct server. We have several production use cases already on that. So it certainly works. It's been in the process of getting stabilized. At this point, it is pretty stable, I would say. We haven't had incidents for a while related to that. But we have not yet pulled the trigger on migrating all thin client users to that. There are certain boxes we want to check before getting there, but that is an ongoing track as well of effort. And then there's a variety of other things, but those are maybe two of the highlights, I would say.
Yeah, absolutely. I think, you know, there's always some things that we cannot cover because of in the interest of time, but it was a good overview of understanding why VeniceDB was created, how it works in terms of write and read path, and what are the query patterns supported, and more importantly, why it was called VeniceDB. So that is also good. So thanks a lot for sharing all the insights. I'm really looking forward to the improvements that you mentioned by the community. And probably we can also do an episode 2, diving deeper into how these different components interact with each other and different read paths and clients and some other advancement that you would work on in the future. So thank you for joining me. I'm really excited that we did this and looking forward to releasing this episode soon. I'll also make sure I add all the important links in the YouTube description so our viewers can look at that and refer to your talks and the blogs and learn more about VeniceDB. So thanks a lot for joining me, and yeah, looking forward to it.
Yeah, if you want to do a take two at some point, I'd love to do that. And thanks for, like I said in the beginning, thanks for all the work you do in the community for sharing knowledge. I think that's really appreciated. I myself have listened to a bunch of the episodes. Although you're quite prolific, it's hard to keep up with everything you come up with. But yeah, thank you for that. And yeah, if anybody wants to learn more, we got the documentation at venicedb.org, and we might do a VeniceCon at the end of June. The details are not finalized yet, but we're trying to organize that. It will certainly be online. I don't know if there will be a in-person part of it as well. But yeah, stay tuned. We might be able to announce that soon.
Absolutely looking forward to it. Thanks a lot.
Cool.